morning, everyone, online and in person. It's my pleasure to welcome Andie de Villiers today as our speaker. Andie did her master's in engineering at Northwest University, and then she did her PhD at the University of Cape Town. And she's been our colleague at Stellenbosch University for the last 5 years. And she's a very nice person to have around, always up for a cup of coffee when she's here, and always giving a great talk. So Andie, I'm going to give over to you to tell us a little bit more about your research.
Good morning, and I'm glad to tell you a little bit about the work I've been doing recently. It's focused on a visco-elastic formulation using the continuum-kinematics inspired peridynamics. But to set the scene, I'd just like to give a more personal motivation of why I'm working on peridynamics. I'm really interested in modeling biofilms. So biofilms are bacteria that adheres to each other and to a surface. And you have to consider the whole life cycle. So there's some growth involved and remodeling. So depending on the environment, the structure or material characteristics differ. And it's also very interesting, well, it's a very hot research topic to know when detachment will take place, or when these pieces of the biofilm will break away. Now, my first approach was to use classical continuum mechanics. And while I was presenting a poster on this at a conference on multi-scale modeling, there were two invited speakers. And the one were talking about peridynamics, and the follow-up was on continuum kinematics inspired peridynamics. And it just felt like this framework was a natural fit for all of these modeling behavior that I would like to capture. The talk of today is also structured in this way. First, a little overview on peridynamics, and then a more technical section on continuum kinematics inspired peridynamics. And this very last section on visco-elasticity is where my contribution lies. So the two most important papers on peridynamics is both by Stuart Selling, the one introducing peridynamics, and the next introducing the concept of state. But even though it was named and introduced by Selling, ideas of the theory can be traced back to the 19th century to applied mathematician Gabriel Paoli. So peridynamics is a non-local continuum theory, but it's different from other non-local continuum theories as the concept of stress and strain is not present. And this is very convenient when you want to work with discontinuities, because if you look at the classical continuum mechanics, the governing equations is written as a PDE. But how do you calculate a spatial gradient over a discontinuity? So that's where the challenge comes in. But peridynamics formulation is an integral differential equation, or the governing equations are written as an integral differential equation. So it's appropriate for problems with discontinuities such as crack and interfaces. And so it's not really surprising that the contributions or the applications that use peridynamics to model damage and fracture has grown exponentially in the last 2 decades. But there's also other applications, and it's suited for multiphysics and multi-scale problems. What is peridynamics? I want to first look at molecular mechanics and continuum mechanics briefly, because peridynamics borrows concepts from both of these modeling techniques. In molecular mechanics, particles, or the motion of particles is really considered from a reference domain to a reference to a current configuration. Now, when we look at the equation of motion, the forces that creates the motion is both external forces, so from out of the particles, but there's also a part that's these interaction forces, so how the particles interact with each other. And this is mainly based on the distance or the stretch actually of the two particles from the one configuration to the other configuration. So maybe it's worth mentioning that the reference configuration is at when time is 0, and the current configuration changes over time. Again, in classical continuum mechanics, a continuous body is considered, and the motion of a point can be mapped by a function such as phi to the spatial configuration. Okay, but if you consider one of these points, the state of this point is influenced only by its immediate neighbors. So it's a local theory. And you can see from this conservation of momentum equation that there's the divergence of the stress. The stress is again related through a suitable material model to the strain, and the strain is a function of the gradient of displacement. And it's these gradients that are difficult to evaluate when discontinuities are present. Okay, so peridynamics is a continuum body, but what happens is the body is divided into material points that occupy space in volume. So it's a non-local framework in that the material points within a neighborhood influences the point you are looking at. And the interaction forces can then be written as an integral. So here we can see how the force on this point is really non-local. So it's an integral over this neighborhood. Okay, so in the original formulation of peridynamics, which is now called bond-based peridynamics, the forces was only dependent also on the stretch. So of this vector between a point and its neighbor, going from the reference configuration to the current configuration. So it's sort of like a spring between two particles. You can view it as that, as a spring between two particles. But from a material modeling perspective, you only are left with this one material parameter. So this restricts the applicability to material modeling a little bit. For example, if you consider elasticity, you always have the Poisson ratio is fixed at 0.25. So for example, in continuum mechanics, there's always these two parameters, the Lemay parameters, that you don't have here. It can also not capture shear deformation accurately. And this is a problem, for example, in shear hardening of plastic deformation. But there has been different ideas to overcome this challenge or material model restrictions. The first by Selling, and he introduced this notion of state. Now, state can be seen as a generalization of a tensor. Here, the pictures is a nice example. So on the left, a sphere is mapped to an ellipsoid with a second order tensor. A state can map the same sphere into a more complicated shape that can even contain discontinuities. So that was the first idea. Then there was also ideas to have the forces of between the material points not only depend on the stretch, but also in the change of angle of this bond. And then the third idea, which I'm talking about now, is continuum kinematics inspired peridynamics. In CPD, the deformation measures mimics the deformation measures found in classical continuum mechanics. So we're in bond peridynamics, only the bond between two neighbors are considered. It's now extended to 1, 2, and 3 neighbors. So the interaction potentials or the energy is decomposed into contributions from 1 neighbor, 2 neighbor, and 3 neighbor interactions. Okay, so now we get to the CPD section. And this is the 2 papers which I found most helpful. The first is very theoretical, and it looks at the thermodynamical basis of the constitutive equations that will result. But then the second paper is more practical, so it's about the numerical implementation. Okay, before we get to the classical continuum kinematics inspired part, let's just look at the classical continuum kinematics part. So there are 3 main measures used in classical continuum mechanics. The first being the deformation gradient. So the deformation gradient can be viewed as a mapping of a vector. So this would be the tangent of a curve from the reference configuration to the spatial configuration. Okay, the second important measure is related to volume, and it's this Jacobian determinant, which can be calculated by evaluating the determinant of the deformation gradient. And then the last important deformation measure is called the cofactor. And the cofactor relates surface elements in the reference and current configurations. Okay, so it's a line, an area, and a volume. Okay, so in CPD, we want to look at deformation measures which mimics this transformation of a line, an area, and a volume. And we also want to recover the kinematics of classical continuum mechanics when this neighborhood shrinks to zero. So when it becomes a local theory again, because that's a big difference. CPD, Peridynamics is non-local. Okay, so it's helpful to define this bond vector. So it's the vector pointing from the point to its neighbor in both the reference and the current configuration. Okay, same story, but now with a nicer picture. We want to find the transformations between line, area, and volume. So it turns out the first important deformation measure to use is this bond vector itself. So the line, the vector between the point and its first neighbor. And if we consider this C, when the neighborhood shrinks, so in the case of a local theory, and we use a Taylor expansion and neglect the higher order terms, we can recover the deformation gradient again. Okay, the second important deformation measure is the finite area element, and this mimics the cofactor. And you can construct it with a cross product of the vector between two neighbors. And then the third ingredient for deformation measured is one that relates to volume, and this can be constructed by a triple product of the three neighbors. And that mimics the Jacobian determinant. Okay, now without too much derivation, I just give you the linear momentum equation, and I will unpack these terms or explain these terms in subsequent slides. But you can see that when you go through all the maths, you get something that looks very similar to classical, the momentum conservation equation in classical continuum mechanics, but again with this non-local interaction force, and it's subject to something that's reminiscent of a traction boundary condition. Also, I show the balance of angular momentum that should be fulfilled. And then, because I don't want to have too many equations in my next slide, I already introduced here the fact that the total potential energy is decomposed into parts from the one neighbor, the two neighbor, and the three neighbor interaction. So the line, area, and related to volume. And consequently, the force density per volume squared is also decomposed into parts associated with one neighbors, two neighbors, and three neighbors interactions. Okay, so from here, I'm just going to show the one neighbor interaction equations. And it's a bit of cheating because the one neighbor interactions, it's really the results boils down to the bond-based peridynamics of all the challenges that goes with that. But you can follow the same process or logic for the two neighbors and three neighbors. It's just more equations. Okay. So I have this aim that I want to look at how to implement visco-elasticity in the CPD framework. So that's why I chose to start with the non-equilibrium thermodynamics. More specifically, I neglect temperature changes, and I look at the power dissipation inequality. It's based on the second law of thermodynamics, and it really just says the rate of the stored energy of the body can never exceed the external power provided to the body, which makes sense, I think. I'm going to further restrict myself to only look at quasi-static processes, where, in other words, where the kinetic energy is neglected. And this means that the external power provided to the system is equal to the internal power due to this interaction forces. so the forces between the particles. Okay, and I want to unpack this internal, maybe expand is a better word, this internal power. But to do that, I'm jumping again back to classical continuum mechanics and talk a little bit about the strain energy function and work conjugate pairs, which I hope is familiar to some of you. So the strain energy function is a density. And if we integrate that over the volume, we can recover the total internal potential energy. And I just write here, it's not that closely related, but I just want to show you also how the strain energy function is used in constitutive equations. So here is the definition of hyperelasticity. So nonlinear elasticity. And you can write, this is a stress tensor called the first Euler-Kirchhoff stress tensor. You can write the stress tensor as the partial derivative of the energy with respect to this deformation gradient. So something that has to do with force, something that has to do with deformation. Okay. For a conservative system, the internal power as a result of these interaction forces is equal to the rate of the internal energy. And we can also write it in integral form. So where this is the rate of the internal work done per volume. And now I get to the real point of the slide. The rate of internal work is usually written in terms of conjugate work conjugate pairs. If you think back about the definition of work, or if you consider the work that a force does on the particle, it's the dot product of the force and the displacement. So here you have something similar, right? So it's a stress measure contracted to a strain measure. Okay, so we want to have a work conjugate pair for CPD. And our deformation measure in CPD is this psi, the vector between a point and its neighbors. Now we introduce the force density vector, which I've shown, but I really only introduce it now as the quantity that's work conjugated to Xi, or the rate of Xi. Okay, so this is nothing new. It's all the old previous slide. Now I want to look at this stored energy density per volume. Okay, and so this is a global quantity, but it's based on the integral of a pointwise quantity. So for each material point, you can calculate this. But you can go even further to look at the neighbor-wise stored energy. Okay, so how this point and its neighbor interact with each other. Okay, and these two are related via the integral over the horizon. Okay, the stored energy is a function of Xi. Okay, and with keeping that in mind, we can rewrite this rate of internal energy as using the chain rule as the partial differential of the stored energy with respect to Xi dotted with the rate of Xi. Okay, that's what I've done here. Okay, so this is the global form of the inequality. So for the whole body. This should also, it's necessary that it also holds pointwise. Okay, so we just take the integrals away. And we can also write it in a local neighbor-wise form. So this is not a necessary condition, but it is a sufficient condition. If this neighbor-wise form is satisfied, the point-wise form would be satisfied. And why I give the neighbor-wise form is we get the constitutive law from this form. So this is how the force density vector relates to the internal stored energy. I just want to go a few slides back to show that it looks vaguely similar to the continuum mechanics case. Okay. We want this well, maybe we take a step back. In classical continuum mechanics, we want to satisfy all the conservation equations, and how we make sure that the angular momentum is satisfied is we require that the stress tensor is symmetric. Okay. For CPD, we also want the angular momentum conservation equation to be satisfied, and we can show that it's sufficiently fulfilled in this energy, stored energy, neighbor-wise stored energy, if we restrict it so that it's not a function of Xi, but on the length of Xi. So then we can have any material model as long as it satisfies this requirement. Okay, now keeping all of these things, I didn't mention something very important. So from this slide to this slide, I changed the inequality because I explained everything in terms of elastic CPD, so there's no dissipation. Okay. And keep all of this in your mind when we move to visco-elasticity in the CPD framework. So I'm going to show you some of the work that I'm doing with Andie de Villiers, and it's also built on another paper by him and co-workers that looks at elastoplasticity. Okay, so now the dissipation is not zero anymore. And we're again looking at the inequality in a global form, point-wise form, and neighbor-wise form. But to include the viscous effects, we extend our neighbor-wise stored energy density so that it doesn't only depend on Xi anymore, this vector between the neighbors, but also on an internal variable, which I call Xi V for viscous. Okay, if we look at this term again, it now has this extra contribution from the internal variables. Okay, if I substitute that back into the global form, it yields my constitutive law and an additional constraint. Okay. Looking more closely to this constraint, can be done by decomposing my bond vector into elastic and a viscous part. And you'll see why now, but I write the length of the elastic part in terms of the total and viscous length. Okay, and this is why. So it can be shown that the angular momentum is sufficiently fulfilled when I restrict my stored energy density to not depend on the whole Xi, but only on the length of my elastic part. Okay, you can write my force density vector using the constitutive equation and the chain rule. And we can see that we can now write it in terms of a value that's dependent on this derivative with respect to the length of E, which is nice because this is a function of the length of the elastic part and the direction. Okay, so that was this first term in my second term. Oh, no, I'm confusing myself. Well, it's this part of the inequality. If we look at the constraint part or the viscous part that's associated with the internal variables, we introduce something called the energetic driving force. And it's also density, and it looks very similar to the constitutive equation, but it's now in terms of my viscous change or length. Okay, again, by using the chain rule, I can expand my definition and write it in terms of the value and the direction. And in fact, the value is the same as that for my force density vector, which is helpful when we calculate things. Okay, so I just now want to show the point-wise and neighbor-wise versions of this constraint, which we get from the global inequality. Now, if you've worked with 1D viscoelasticity, this would look very familiar. Okay, so it looks almost exactly the same as the constraint on internal dissipation if you consider a generalized Maxwell model. We can approach it the same way that we would do 1D viscoelasticity. And how we do this is we need a complementary evolution equation. And this equation describes how the viscous effect unfolds. And the evolution equation should satisfy this constraint. Okay, so I've used a generalized Maxwell model with a linear viscous part. It's a linear relation of the viscosity. And it's very convenient because there's a closed form, fairly simple closed form solution for this linear evolution equation in the form of a convolution integral. But I give you the time discretized version of this convolution integral, which is a recurrence update formula, which is really not too difficult to implement. Okay, so a bit of one slide on implementation only. So it's implemented for the test cases. We've only implemented in MATLAB, really using a collocation method where the quadrature points are at the same point as the material points. And it is nonlinear equation, so we use the Newton-Raphson method to solve this equation. And there was a few things that we needed to develop for to illustrate creep, stress relaxation, and cyclical load. Okay, so let me show you the benchmark examples. The first is where we take a 2D block of a viscoelastic material and we subject it to a constant force. Now, if it was like a purely elastic case, we would expect some deformation that would stay constant. But because of the viscoelasticity nature, we see that we have this initial stretch, but then we also see this creep, and our code and theory capture this qualitatively at least very nicely. Okay, the second benchmark example is cyclical loading. So we take the same block and we now subject it to displacement boundary conditions, cyclical displacement boundary conditions with this amplitude increasing for each cycle. And here we can see it's the stress, a stress measure plotted against a strain measure. The hysteresis very nicely. So what hysteresis is, the loading and unloading, the material follows different curves. So in elasticity, you'd have the same curve. As you unload the material, it will go through the same path. There's another thing that we can see from this benchmark example. If we plot the stress measure against time, at this point, there's no, the displacement is 0, but the stress isn't 0. So it takes a while, and we call this stress relaxation to go again to the equilibrium point. Okay, and then the last example is also cyclical loading, now of the same amplitude, but by shearing the block. And we see it's also a very good qualitative comparison to what's in the literature. Now, what to do from here? First, I have to finish this paper. And what's still necessary is to have sort of like a quantitative comparison to 2D viscoelasticity, but it's a bit difficult because it's not really, you can't really use commercial software to find FEM results because it's not plane strain or plane stress. What you're looking at, you're really looking at 2D viscoelasticity. So that's one thing. In parallel, we're actually busy with an interesting project, which is to investigate when do these bonds fail. So at the moment, in both molecular mechanics and peridynamics, this criteria is strain-based. In other words, if the points or the particles are far enough from each other, you cut the bond. Okay, so there's an implementation, but that's not really physical. So what we're looking at is to rather have energy-based criteria, because so if a material fractures or if the crack elongates, you need some energy for surface creation. So that's also something we're investigating. And Then the rest is really open. There's so much more that could be done, looking at it from a Eulerian perspective to model flow and then fluid structure interaction. And because of the non-locality, it would really be nice in applications where mechanobiology is investigated. So how cells change based on the mechanical environment. And it's not very efficient yet, so there's some work on the numerical implementation that could also be done. Okay, thank you.
Thank you so much, Andie, for a nice presentation. We are going to open the floor for questions now.
Providerman asked, how do I treat the convolution integrals? Do you mean how to get them or how to compute them? Oh, with this. So we do time discretization based on Simpson's rule, and you get this. This is what you put in your code. It's a recurrence formula. So it's really based on the value of your energetic force, but then it's really, I choose this as 0.
Every step you compute one and then update it.
Yes, yes. So it's a history variable. If this was 0, you just have elasticity again. So for each time step, you just update this energetic driving force. You also had I don't know.
Questions on Stellenbosch side still? Maybe from, so sorry.
You mentioned earlier the visco-elasticity, the elasticity, there was inequality side, and then we moved to visco-elasticity with equal.
The other way around. So in elasticity, there's no dissipation. So the energy is it's not lost through heat and things like that. There's no dissipation. So if you take an elastic material and you do anything with it and you take away the forces, it will go back to its original shape. With viscoelasticity, this is different. It will go back to a new equilibrium, but not immediately. It has this history dependence. The viscous part.